Okay, I wanted to walk you through some of my thought process for the first problem that is posted on the whiteboard today, or I guess the first two problems, and make sure that everybody feels good with them. So first one, we're given a rate law. It is second order in total, first order with respect to A, and first order with respect to B. We want to know what the concentration of A is after 5 minutes. And anytime you are asked for a concentration after some amount of time, you need to think to yourself, integrated rate law. A question that I was getting asked a lot is, do I have to memorize these? The answer is no, they are on the formula sheet, which is posted on the agenda. You should also have a copy of it. The problem is that I don't know what the integrated rate law is when the rate is dependent on two concentrations. It might be fun if you figured it out on your own. You could also look it up. It has a lot of natural logs. It's a little bit ugly. You can definitely derive it with calculus that you know, though. So what we could do is assume that this is a pseudo first order reaction, which essentially means that one of our concentrations is going to be way higher than the other concentration. So in this case, 5 molar is many orders of magnitude bigger than 0.01 molar. So what we can do is that we can assume that the concentration of B at any given time is approximately 5 molar. What this means is that we can take our rate law from before and we can plug 5 molar in for the concentration of B. And then we can come up with a new rate law that is pseudo first order. And what I'm doing is I am lumping the 5 molar because now that's a constant. So I'm lumping that in with the rate constant to create some new constant here. And here we have now a first order rate equation. Because it's first order now, we know that natural log A equals log A naught minus KT. The, I guess, kind of confusing part here is that this is now your new K that you are going to be plugging in for here. From there, you just solve it. So I did natural log 0.01 minus 0.01635 times 600 seconds. I got negative 14.45 in my calculator. To undo natural log, you raise both sides. You take both sides, you do e to the power of that side of the equation, and we're left with A is equal to 0.49 times 10 to the negative 7 molar. It kind of makes sense. It should be smaller than whatever concentration we're starting with. 10 minutes is rather long compared to our rate constant, which is on the bigger side of small. Okay, so that's how you do the first one. Second one, we're given a rate law. We have the reaction A, which is a gas turning into the products. And we are asked for the initial rate, specifically in units of molar per second. So problem is here that we're not given the concentration of A. We're given the initial partial pressure. For our units to line up, we need the concentration of A in molarity so that we can have our rate be in molar per second. So what we need to do here is turn atmospheres into molarity. To do this, we're going to use the ideal gas law, and we're going to rearrange for N over V, which is moles over volume, moles over liters, which is equal to molarity. So concentration of a compound is equal to the pressure divided by R times T. You want to make sure that you use the correct R, which is going to be 0.08206 liter atmospheres per mole Kelvin. If you use this as your R value, you want to make sure that your pressure is in atmospheres and your temperature is in Kelvin so that all of your units cancel out. So atmospheres cancels, Kelvin cancels, and we're left with moles per liter. From there, this is a more straightforward problem. We're going to plug our initial concentration of A into the rate law and solve, and we should get a rate of about 1.33 times 10 to the negative 5 molar per second. Okay, so hopefully that helps you out a little bit. There's also some slides with some less computational based questions on the agenda. I will come into school a little bit earlier on Monday, so if you have any questions and you want to ask me in person, I will be in my room. Okay, have a fantastic weekend, and I will see you on Monday.